Welcome everyone to the National Astronomy Meeting 2021, such an important event in the yearly calendar of the Royal Astronomical Society. We're truly honoured to be hosting this event at the University of Bath. We were, of course, planning to host it a year ago, to coincide with a very special date for the RAS, its 200th anniversary, but sadly we were forced to put everything on hold because of COVID. What we've gained over the past year is an appreciation of just how successfully one can run a major event such as this from afar, using the latest virtual conference technology. So though it will be wonderful to welcome you all on campus, it's with genuine pride that we launch NAM 21 as an online event. I've every confidence that this will be as exciting and engaging a conference as the one that we would have run last year, with the added bonus of being more inclusive and leaving a far smaller carbon footprint than an event to which participants would have needed to travel. The RAS and university have put together an excellent programme for the days ahead. As a fellow physicist and engineer, I'm particularly excited by the scientific programme and the wide range of cutting-edge science and technology that will be presented through the week. There will also be an inspiring programme of public engagement activities, from a session where you can explore how comedy techniques can be applied to science presentations, to a workshop where you'll hear insights from scientists, artists, and arts facilitators and what makes for a successful art-science collaboration. Bath has many links to astronomy, making it a most fitting choice for the RAS annual meeting. As you will no doubt all know, the brilliant astronomers William and Caroline Herschel spent much of their adult lives in Bath, and the city is home to the Herschel Museum of Astronomy. As a former member of the Herschel Museum Board, I feel especially connected, therefore, to the themes of NAM 21. Our university is home to distinguished departments in astrophysics and engineering, making this conference particularly important for many of our scientists. I would like to thank and congratulate all those who've been involved in the scientific organising committee, particularly the two co-chairs, Professor Carole Mundell, Head of Astrophysics, and Professor Catherine Mitchell, Director of the Centre for Space, Atmospheric and Oceanic Science. May I also thank members of the local organising committee, in particular Chair Dr. Patricia Shaddy, for all their hard work in these challenging times. In addition, I'd like to thank the Bath students who'll be on hand to provide technical support during the conference's virtual room meetings, as well as colleagues at the RAS, the university's communications team, and our public engagement team, whose innovative approach to the conference means the work presented will reach an audience that goes far beyond the UK's astronomy, astrophysics, and space science communities. Finally, I'd like to say how pleased I was to hear the government's recent announcement of a new award, the RAS Caroline Herschel Medal, to celebrate outstanding research by women astrophysicists in the UK and Germany. The timing of this award, just weeks before NAM 21, could not have been more perfect. I'm really looking forward to an exciting few days. Please do enjoy yourselves, and I hope to welcome you to Bath in person in the future. Thank you very much.
Good evening, distinguished guests, colleagues, friends. It's my great pleasure to welcome you this evening to the Presidential Address. My name is Professor Carole Mundell. I'm Head of Astrophysics here at the University of Bath and Professor of Extragalactic Astronomy. I'd like to take a few minutes just to describe the journey that has brought us here tonight. In 2016, when the RAS first approached me and asked me if Bath would host the bicentennial celebrations for the founding of the Royal Astronomical Society, it was with trepidation that I said yes. My astrophysics research group was brand new. There were only 3 of us, myself, Dr. Carolyn Vilforth and Dr. Steinwutz, the founding members of our group, and we were yet to look forward to see what would come in 2020. But it was the then Vice-Chancellor Professor Dame Glynis Breakwell who encouraged me to take that leap of faith. And with incredible colleagues in the university, we began to prepare for a major in-person conference on the far distant horizon of 2020. We worked hard, my research group grew. We now have a burgeoning and thriving research group of academic staff, postgraduate students, postdocs, and of course today helping us out as well, our master's students. But we could not foresee what would actually get in the way of having that in-person conference, which we had intended to hold last year. And right up until we had to postpone, we fully intended to go ahead with that. And so we've learned, we've spent the last year working incredibly hard, and I must pay tribute to all of my colleagues, students, staff and friends at the University of Bath and at the RAS who've helped us to get here tonight. We've learned a lot, we've had a few glitches along the way, and in particular, I'd like to pay tribute to you, the delegates at the conference and the fellows of the RAS who have supported us in this journey. It's wonderful to be able to connect with you all safely and digitally over this week. Many of us have not seen one another for some time. Many people have been working with all sorts of personal challenging difficulties in the background for over 15 months, not least of all our students trying to finish their research projects. And so it's with real celebration that we hold this inaugural, this presidential address this evening and have our digital conference, which is the inaugural digital conference of the Royal Astronomical Society. This to me seems incredibly apt, given that we're celebrating the 200th year of the Royal Astronomical Society, and we look forward to 200 more wonderful years of technological and scientific breakthrough and discovery. Tonight, it is with great pleasure that I introduce our president, Professor Emma Bunce. Emma is head of the School of Physics and Astronomy at the University of Leicester, and she is the Royal Astronomical Society bicentennial president. She is a world-leading planetary scientist, and she's been involved in multiple space missions exploring our solar system, including Cassini at Saturn, Juno at Jupiter, Bepi Colombo at Mercury, and the future Jupiter Icy Moons Explorer JUICE mission to Ganymede. She uses data from these missions in a variety of ways to answer fundamental questions about these diverse solar system objects. She's principal investigator on the Mercury Imaging X-ray Spectrometer, part of the Bepi Colombo payload, which launched to Mercury in October 2018. Having played a key role in the definition of and proposal for the JUICE mission, she will analyse these exciting data from the 2 instruments when the mission begins in 2030. She has received multiple awards in recognition of her outstanding work, including the 2018 Royal Astronomical Society Chapman Medal for her research on gas giant planets. Tonight, she will speak to us for about 45-50 minutes. She will give a world-leading science talk. We do encourage you to put questions in the chat. I will be picking those up and putting them to her at the end of her talk. And after that, we invite you to join us on a broader fireside chat where we'll explore wider aspects of science and innovation and scientists in our fireside chat that will go on till 8:25. So do join us for that conversation, because I'm sure that will be very interesting. I'll hand over now to Emma and look forward to hearing her talk and meeting with you again when we get to the questions and answers. Emma, over to you. Thank you.
Thank you so much, Carole, for that wonderful introduction. I'm just pressing buttons whilst I speak, and hopefully I've shared my screen. Just going to move that out of the way. So hopefully you can all see my PowerPoint screen, and hopefully everyone can hear me okay. So thank you, Carole, for that wonderful introduction. It's really such a pleasure and an honour to be able to give the 2021 presidential address during this very special NAM meeting, which Carole has just outlined. So thank you for allowing me the opportunity to do this tonight. And Carole and I are going to chat more after the talk. So I'm just going to get straight on with my talk and say good evening, everybody. And this evening, I'd like to talk to you about the topic of our future exploration of Jupiter, and specifically Ganymede. And this is quite a topical subject for a couple of reasons. First of all, you may have seen in the news recently that the Juno mission has just performed its first close flyby of Ganymede. Now, those that are familiar with Juno may know that the spacecraft is actually in a polar elliptical orbit of Jupiter. That means it has a very close periapsis pass of Jupiter. We're talking a few thousand kilometers above the cloud tops. And that periapsis point of the orbit was initially located very close to Jupiter's equator at the start of the mission. But because Jupiter is oblate, that means it has a larger radius at the equator compared to the pole, the orbit has precessed in latitude such that the distant equatorial crossing distance, initially which was 100 Jupiter radius away, has moved closer and closer to Jupiter as the orbit periapsis has moved northward. All of this means it provides a really exciting opportunity for Juno to fly past some of the major moons of Jupiter, namely Ganymede, Europa and Io, during the Juno extended mission, which is a whole separate talk, which I won't give today. So Juno's closest approach during perigove number 34 on June 7th, 2021, was just over 1,000 kilometers above the surface of Ganymede. That's the closest that any spacecraft has been to Ganymede for 20 years. Now, some of the pictures that you can see on the slide here, one on the right-hand side is from the orbiter's JunoCam imager, and the other is from its Stellar Reference Unit star camera. That's the middle square picture. That picture was actually taken on the dark side of Ganymede, and so what you're actually looking at there is light reflected from Jupiter. So these pictures show the surface of Ganymede in remarkable detail, including impact craters, clearly distinct dark and light terrain, and also long structural features possibly linked to tectonic faults. So the Juno team are busily working on the data beyond images as well, different data sets, and we can look forward to seeing what they find in the coming weeks. But what strikes me about these images is that they only tell part of Ganymede's incredible story. What you can't see from these images is the magnetic field that the moon Ganymede generates within its core. You cannot see the miniature magnetosphere that forms in the flow of Jovian plasma and magnetic field. You cannot see the aurora that Ganymede has in its polar atmosphere, and perhaps most tantalizing of all, you cannot see the evidence that hints at a vast global ocean underneath the thick ice crust. It's a pretty spectacular planetary object. So let me tell you briefly about the mission that is going to tell us more before I go through some of the details of what we think might be going on. So I'm going to talk about a space mission now which is very close to my heart, as you heard at the beginning, one I was fortunate enough to be involved with helping to define from the very start. And that was a long time ago. Interplanetary robotic exploration is a very long process, provides many challenges, and patience is certainly a key for everybody involved. So here are the basic facts. JUICE, the JUICE mission, as it's known, the Jupiter Icy Moons Explorer, is a European Space Agency only mission whose focus is exploration of the Jupiter system. And it has two overarching science themes, which you can see on the right-hand side. That of emergence of habitable worlds around gas giants, and a thorough investigation of the Jupiter system as an exemplar for gas giants. The JUICE concept is that of a European-led orbiter, and it's a spacecraft which will orbit first Jupiter, and it will characterize the moons of Europa and Callisto through flybys, and then focus on Ganymede with a dedicated orbit at the end of the mission. So it's going to be the first spacecraft to orbit an icy moon, focusing on Ganymede towards the end of the mission with an approximately 9-month dedicated orbit. So personally, I'm really very excited that this mission, after so many years of work, ESA's first L-class mission, is nearly ready for launch. It's going to be launched next year in 2022. And that's the second reason why I think this is topical tonight. And incredibly, that last intense period of work, the instrument build and delivery and the spacecraft integration has taken place despite a global pandemic. And I'll touch on this at the end of the talk. So, as I mentioned, a major science focus of the mission is to explore and characterize the habitability of the moon Ganymede, and to a lesser extent, Europa and Callisto. And this was a clear aspiration of ESA's cosmic vision. Now, in this picture, I'm showing what is now commonly accepted, that there should be 2 habitable domains in every stellar system. A very narrow one, sometimes known as the Goldilocks zone, where water can exist in liquid form on the surface of a planet, such as here on Earth. The position of that domain then is driven by the temperature variations as you move away from the star. And this requires that the surface habitats, if they indeed exist, will be closer to the star. But there is also a much larger, potentially habitable domain, a zone where water is extremely abundant and where liquid water could be found in deep reservoirs or oceans, a sort of new Goldilocks zone. That second domain is beyond the snow line, which at distances from the star where the temperature is below the freezing point of water. And in this domain, water is as abundant as silicates in the form of ice and also in the form of deep liquid layers in the subsurface. So of course, the Jovian system sits out in this domain, and JUICE, by its exploration of Ganymede, Callisto and Europa, is going to be able to explore the habitable zone beyond this snow line, and hence paving the way for our understanding of what makes a planetary object habitable in this region of our solar system. At present, it's thought that there could be as many as 9 ocean worlds within our solar system, though it's possible there could be even more. We need further exploration of the outer reaches of our solar system. So those objects are minor planets Ceres, Europa, Ganymede, Callisto, Enceladus, Dione and Titan in the Saturn system, Triton, the moon of Neptune, and somewhat surprisingly, Pluto. So I'd like to now explore this idea of ocean worlds in a bit more detail. How is it possible to have liquid water so far from the sun? And how do we know that it might be there? So those are 2 key points that I just want to touch on. So as I just mentioned with reference to the previous slide, we need heat in order to enable liquid water to exist on the surface, or for liquid water to exist at all. And we know that in order to help ice to melt, we need a source of heat. So what is the source of heat for the Galilean moons of Jupiter? They're beyond the snow line, so it's not the sun. And so I'm going to just briefly explain the 2 possible sources. So here I'm showing you the Galilean moons. They're in order: Io, Europa, Ganymede and Callisto, but the picture is not at all to scale. So I just want to show you the interesting effect that takes place within this system. So the orbits of Io, Europa and Ganymede, and you can see with the orbital period numbers here, they actually form a pattern known as the Laplace resonance. So for every 4 orbits that Io makes around Jupiter, Europa makes exactly 2 orbits and Ganymede makes exactly 1. And this resonance causes the gravitational effects of the 3 large moons to distort their orbits into elliptical shapes. So that's because each moon receives an extra tug from its neighbours, as you can see in this little animation, at the same point in every orbit. The tidal force from Jupiter, on the other hand, also strongly affects the moons, but would work to circularize their orbits. So crucially, that eccentricity, this resonance that allows the orbits to stay eccentric or elliptical, causes regular flexing of the 3 moons' shapes. So with Jupiter's gravity stretching them out as they approach it, and then allowing them to spring back as to more spherical shapes as they swing away. And this is shown in this rather exaggerated little animation at the bottom here. So this tidal flexing is what provides the heat to the moon's interiors as a result of tidal friction. So this is seen most dramatically in the extraordinary volcanic activity of the innermost moon, Io, and that's of course closest to Jupiter and hence subject to the strongest tidal forces. And it's thought that tidal flexing amplitudes could be up to 100 meters of the surface actually moving. And then at Europa, a little further away, again, the surface motion, the tidal flexing amplitude at Europa could be up to 30 meters, so a significant amount. For Ganymede, it's thought that the amplitude of the solid tides could be around 7 meters, but this has yet to be verified. And this is something that the JUICE mission is going to be able to do. Another possibility for the heating is radiogenic heating, where the radioactive decay of elements within the moon's rocky mantle results in production of daughter isotopes and the release of radiogenic heat. Now, for Ganymede, some models suggest that even without tidal flexing, there could be enough radiogenic heating to produce a liquid layer. So, of course, the retention of heat is possible thanks to the icy surfaces, and I'll come on to that in just a moment. Those thick icy crusts that form the outermost shell of the Galilean moons Europa, Ganymede and Callisto are able to insulate any liquid layers underneath from freezing. Okay, so how do we know, or how do we think we know, what possibly lies beneath these icy crusts at the outer planet moons? So we have the sources of heat, tidal flexing, and a possible addition of radiogenic heating in the interior. But I want to just very briefly in one slide gather the evidence that's been gathered over many years that hints at the presence of an ocean, and really just to talk about the various techniques that are involved. So, and that's in addition, actually, I should say, to high resolution imaging that also gives clues about the geologic activity on the surfaces. So measurements over the years have come from ground-based telescopes, flybys from the Voyager mission, and the Galileo orbiter mission, which undertook 6 close flybys of Ganymede during its time in orbit in the 1990s, and now, of course, Juno in 2021. So the first technique is spectroscopy. So essentially a technique which enables us to work out what something is made of. And interestingly, back in the 1960s, spectroscopic telescope observations actually allowed the detection of the icy surfaces of the Galilean moons for the first time. The next closer views from the surface came from robotic interplanetary spacecraft, from Voyager and from Galileo, and they provided magnificent first close-up views of the surface, allowing the detection of additional features in the surface composition. So, for example, Galileo NIMS measured the presence of salts on the surface, which gives, again, some evidence of a possible saline ocean beneath. The second technique is the measurement of the gravity field, so gravitational field measurements. And those were first measured at close range by the Galileo mission flybys of the moons in general, and specifically we're focusing on Ganymede. So for Ganymede, the results confirmed that the interior is differentiated. So that's where the body has developed into compositionally distinct layers. And also that the layers of variable density actually exist throughout Ganymede. And the measurements also allowed the size of those layers to be estimated. The data strongly suggested the presence of a dense metallic core, and also suggested the presence of water and ice layers of lower density in the outer regions. The third technique is using the magnetic field, and the focus of the main part of the rest of my talk. And the measurements of the magnetic field, again, taken during 6 close flybys of the Galileo spacecraft, revealed some remarkable facts about Ganymede. The first is that the complex magnetic field measurements indicate that Ganymede has an internal field, and some measurements hint at the presence of an ocean, and I'm going to explain that in a little bit more detail in the next few slides. So on the right-hand side is the picture that we have of Ganymede's interior as it possibly may look. A fully differentiated body with an iron core, which is then the possible source region for the dynamo field, a rocky silicate mantle and an ice mantle in the outer layers. The magnetic field measurements then suggest that a layer of liquid water could reside sandwiched between a deep layer of ice and the ice crust, so a sort of ocean sandwich, if you will. So I've already described how the gravitational interactions of the giant planet and its moons provides a source of heat to the interiors. But as I've already hinted at, another type of interaction is key to understanding the possible ocean layer below the subsurface. So a little bit of context then. The Galilean moons are actually embedded within Jupiter's extended magnetic environment, the magnetosphere. And Jupiter, perhaps unsurprisingly, has the strongest internal magnetic field in the solar system. And it actually rotates the magnetic field with Jupiter at Jupiter's rapid rotation rate of around 10 hours. It's very fast rotation. Thanks to the active volcanoes, which I've just described, and you can see a little movie of that taken by New Horizons at the bottom, Io also serves as a major source of plasma for this magnetic environment. It actually produces around a ton per second of plasma into Jupiter's magnetosphere. So the plasma field, rapidly spinning magnetosphere, becomes distended into what we call a magnetodisk. And this region, the magnetodisk, is characterized by cool, dense plasma collected near to the magnetic equator as it's spinning around, and very radially stretched magnetic field lines. So that's the environment that the Galilean moons are orbiting around Jupiter within. A very dynamic and interesting environment. But there's one more really key fact, and that's that the magnetic field of Jupiter is actually tilted at about 10 degrees with respect to the rotation axis. And this is key and potentially key to the measurement and discovery of subsurface oceans, and I'll describe that in a moment. This tilted magnetic field of Jupiter means that the conditions near to Ganymede, let's say, especially the density of the upstream plasma and the magnetic field orientation, actually varies as the magnetodisk rocks up and down in latitude across Ganymede as Jupiter rotates. On the right-hand side, you can see a projection of the Galileo trajectory onto the equatorial plane, which runs all the way through to the end of the mission in 1999. You can just about make out the orbital paths of the Galilean moons in light blue. So the periapsis points, all I wanted to show with this picture actually was that the periapsis points of these orbits coincide with the moon locations, and of course that's done entirely on purpose as the major focus for this mission, but it also helps to steer the spacecraft through gravity assist maneuvers throughout the lifetime of the mission. Okay, so I would like to next give some insight into the possible ocean detection from the magnetic field observations that was made by the Galileo team, and that team was led by Professor Margaret Kibbleston. Margaret Kibbleston was the magnetometer PI for Galileo, and she is also one of our recent RAS Gold Medal winners. So remembering that Galileo made 6 close flybys of Ganymede at various locations in latitude above Ganymede, and also at various phases of that dipole rotation, having some quite variable conditions then for those flybys. Professor Kibbleston and her colleagues had quite a job on their hands to unravel what was going on. And they made some significant breakthroughs in our understanding of the Ganymede magnetic environment. Now, during the very first flyby, and published by Kibbleston in 1996, something quite incredible was discovered. Now, it's useful to note that at the orbit of Ganymede, we would expect to see, if nothing interesting was happening or nothing exciting was happening, we'd expect to see the background field of Jupiter itself. And that's roughly a combination of the internal field and this magnetodisk field, which I just described. And the strength of that field near to Ganymede's orbit is around 100 nanotesla. However, during that first flyby, a field of hundreds of nanotesla was observed as Galileo swooped about 850 kilometers above the surface. It was seen that the field strength increased to a maximum and then decreased with 1 over the radial distance cubed, which is strongly suggestive of a dipole magnetic field. So the team had discovered that Ganymede generates an internal magnetic field, which was obviously a huge surprise, and the only moon that we know in the solar system that does so. This magnetic field was found to point northward at the equator, which is opposite to the direction of Jupiter's internal field, which is also very interesting. This Ganymede internal field was measured in more detail during the later orbits, and Margaret Kibbleston and her team found that the field was consistent with a dipole equatorial field strength of around 850 or 800 nanotesla, and also found that that strength of magnetic field was strong enough to hold off the Jovian magnetic field in plasma, and thus creating a miniature magnetosphere within the larger Jupiter magnetosphere. And you can see a sketch of this in the middle of those three pictures. So this is the internally generated field, and this is the magnetosphere field that was discovered by the Galileo team. And that's also unique within the solar system. Now, what's different about Ganymede's magnetosphere is that it sits within a subalphanic flow. This is meaning that the alphane Mach number is less than 1, and therefore the magnetic field of the upstream flow, that's the Jupiter flow of plasma and magnetic field, shapes the magnetosphere, so that the magnetic field shapes the magnetosphere and not the plasma flow. And this gives it a distinctive shape, which I'll show you in the next couple of slides. That subalphanic flow also means that there's no bow shock that forms upstream, but there is a magnetopause and a magnetopause current system which is present, and the familiar sharp rotation of the field at the boundary was observed by Margaret Kivelson and her team in the Galileo data. Now, by the end of the mission, and following Margaret's team's work at Europa and Callisto, discovering magnetic field signatures indicative of a subsurface ocean, all of the Ganymede data were then assembled and analysed to see if the signature of an ocean may well be present at Ganymede too. So how does this work? So you may well know that the change of magnetic flux through a conductor, or the motion of a conductor through a magnetic field, generates electric fields and thus also electric currents in the conductor itself. The changing electric fields and electric currents are the source of secondary magnetic fields, and those are called induced magnetic fields. The primary time variable magnetic field is called the driving magnetic field, and in this case, that's the field of Jupiter rotating past Ganymede. So if an ocean or a shell of conducting fluid was present in the interior of Ganymede, then it would be possible to generate an induced field strong enough to be observed, and it's possible to detect the subsurface ocean signature as Jupiter's background field rotates, applying a changing driving field direction. So that's again this tilt of Jupiter's magnetic field, changing the direction of the driving field as it moves across the moon. And I'll describe that more in just a moment, and you can see it written on the slide there too. Now, Margaret Kivelson's team's very careful work, published in 2002, demonstrated that the evidence was inconclusive. It was shown that Ganymede's magnetic field could be equally explained by a dipole plus a higher order quadrupole term, which would have a more complex spatial structure at various latitudes of the Galileo flybys. But it could equally be explained by a dipole magnetic field plus a time-varying induced magnetic field signature. So the results were inconclusive. Now, to distinguish between a quadrupole and induced magnetic fields requires separating the spatial and temporal effects from those flybys. And that's obviously very difficult to do with just 6 flybys from Galileo. And Kivelson's papers point out that you really need an orbiter in order to be able to do that. And of course, this is where JUICE is going to come in. Okay, so the picture that you can see on the top left here is actually, it's for Europa, but the principle is the same, and is showing that the induced field, which is given the direction of which is pointing in along this blue arrow, is oppositely directed to the inducing field, the driving field of Jupiter. So this is the magnetic field line which is pointing away from Jupiter in the northern hemisphere and would point back towards Jupiter in the southern hemisphere. Now, if Ganymede has a conducting subsurface ocean, then this will change direction as Jupiter rotates, and the driving magnetic field changes from outward pointing to inward pointing, depending on whether Ganymede is above or below that magnetic equator. Again, it's all coming back to the tilted field of Jupiter. The field also changes with other variations due to, first of all, Ganymede's orbital position within the magnetosphere. So as Ganymede orbits around within Jupiter's magnetosphere, you find that the magnetosphere is asymmetric with local time, and so that changes the conditions. And it's also possible that the driving field will change with dynamic events like solar wind dynamic pressure. Now, in fact, these frequencies of the changing driving field are really important. In fact, they're key to not only the measurement of the potential subsurface ocean, but also its properties like its depth and the thickness of the ice shell, also combining with modelling work. So we require measurement at the multiple frequencies in order to have the chance to help define those characteristics. So the timescales for the variations, or the driving frequencies, actually drive the length of time that you want to put an orbiter around Ganymede for. So the JUICE mission, or the Ganymede orbit part of the mission, the close orbit, which I'll show you later, was the length of time is driven by these frequencies of possible variations. So I'll come back to that a little bit later. So prior to the Galileo mission, a lot of work had been done on the interaction of conducting both magnetized and non-magnetized moons. And so conducting moons could mean that there was an ocean or an ionosphere or some sort of confined magnetic field like Ganymede has. And this was considered and published in famous papers in my field by Neubauer in 1980 and Southwood in 1980 as well. And David Southwood is previous president of the Royal Astronomical Society. And because of the subalphanic interaction I described in the previous slide, the shape of this interaction region is defined by the magnetic field. And this alphane wing interaction depends on the plasma density, and as such, it maximizes at the center of the magnetodisk. So again, it depends, the angle of the alphane wing interaction depends on the phase of the dipole relative to Ganymede, and whether Ganymede is within the magnetodisk or above it or below it, and that changes the shape of the magnetosphere. And I think you just saw that cycle through on the right-hand side whilst I was talking. So the magnetosphere is shaped into something more cylindrical than the usual bullet-shaped morphology that we see for the Earth and for Jupiter. And the angle changes as the Moon experiences various background field orientations and various plasma densities. And the picture on the right comes from the work of Shinja Jia at the University of Michigan, which I forgot to write on the slide. So I think it's fair to say that the overall picture is quite complex. Ganymede has an internal field, which may have a dipole, and it possibly has quadrupole components, which would give spatial variation in latitude. It has a magnetosphere and the alphane wing interaction, whose morphology changes with Jupiter rotation period, and also the potential for an induced field whose magnitude and direction will vary with changes in the driving field strength and direction. So the magnetic field variations that we're talking about are actually relatively small for the various frequencies of changes. So just to give you some insight then, we're talking about a few tens of nanotesla for a 10.5 hour frequency. So that's the field that would be modified by Jupiter's rotation rate, down to just 1 or 2 nanotesla changes for the longer frequency. So that's the Ganymede orbital position around Jupiter and solar wind dynamic pressure variations. So that's incredibly demanding in the background of the strong magnetic field of Jupiter and the complex magnetosphere interaction. So we're going to need a very fantastic magnetometer on as long a boom as possible in order to make this happen. And I'm going to show you a little bit about the instrument involved in the next couple of slides. So I mentioned already that Ganymede also has aurora in its oxygen atmosphere, and this was first discovered by the Hubble Space Telescope and first imaged by Feldman et al., and that's the picture there from the Feldman paper. And you can see that there are 2 circumpolar auroral ovals which are situated in the north and south polar regions of Ganymede. Pretty incredible. And Melissa McGrath also studied these auroral data and found that the auroral ovals are at higher latitudes on the leading hemisphere and at lower latitudes closer to the equator on the trailing hemisphere. Now, more recently, in 2015, this is the central picture and the artist's impression on the right-hand side. A colleague of mine, Joachim Sauer, and his colleagues did some really neat detective work, I think, looking at Ganymede's auroral ovals with the Hubble Space Telescope over multiple Jupiter rotations. As we've just discussed, that magnetosphere, the miniature magnetosphere of Ganymede orientation changes with rotation of Jupiter due to the tilted internal magnetic field of Jupiter. And that would cause the auroral ovals to rock back and forth in their position too, given that they are the product of that interaction. Now, Sauer modelled the response with or without an ocean. So with or without an induced magnetic field present. And without the magnetic field due to an ocean, we'd expect the oval to rock by just a couple of degrees. Without the ocean field, we would expect the rocking to be 6 degrees, and with it, we would expect it to be reduced to just 2 degrees. So their observations actually found to be consistent with the presence of an ocean. So this has offered a very valuable new technique for remote sensing the presence of an ocean. But it does seem that you have to have a pretty good idea of what you think is happening already. Okay, Ganymede's magnetosphere is a conducting obstacle that interacts with the flow in the Jovian plasma and magnetic field, and that interaction creates Alfvén waves and field line currents that flow along the magnetic field lines between the Moon and Jupiter's polar atmosphere. And I'm not going to dwell on this, but it's always just fantastic to have a look at Jupiter's main auroral ovals. This is from the northern hemisphere of Jupiter, taken by the Hubble Space Telescope, and you can see a main auroral oval and a bit of a mess on that side. And then you can see an Io spot and footprint, and then we have Europa and Ganymede's footprint. So this is the auroral footprint of Ganymede, and that footprint in the aurora of Jupiter's atmosphere actually relates to the magnetosphere interaction with the Ganymede magnetosphere itself. So that's a really interesting topic all by itself. Okay, in the interest of time, I'm just going to keep moving. So one of my favourite papers that I read a long time ago now, and I think is really intriguing, is a result from Krishan Khurana et al. In 2007. And they suggested that there is actually a notable difference in the surface brightness, or the albedo, at high and low latitudes on Ganymede. You can see it in this image, really. We've got a darker region at lower latitudes and a lighter region at higher latitudes. And these coloured lines actually indicate the locations of the open, closed magnetic field boundary. So that's about this point in here, where the field due to Ganymede is no longer closing from one hemisphere into the other, and instead opens out and connects with Jupiter's magnetic field. So the idea then is that in this case, the Jovian plasma is able then to precipitate along these open field lines and is somehow interacting with and modifying the surface of Ganymede itself. So I'm now just going to talk quite briefly about how JUICE is going to tackle this particular science topic. I mean, I've just talked about one aspect of the science that JUICE is going to be able to do. And it's just one technique or one way of assessing the presence of an ocean and hence habitability. So the mission timeline looks like this. The launch is going to be in 2022 and will arrive in the Jupiter system around 2030. So it's quite a long transfer between the Earth and Jupiter, but in planetary science, we're pretty used to that. And so then after the transfer, we will have Jupiter orbit insertion, and we'll have, first of all, the Jupiter system phase. So this is when JUICE will be orbiting Jupiter itself. And as well as studying the planet itself and the magnetosphere, it will also have close flybys of Europa ×2, and also many flybys of Callisto during the mid-inclination phase, and also many flybys of Ganymede leading up to the reduction of the orbit, actually, so reducing that orbit down to the distance of Ganymede, ready for orbit insertion around Ganymede itself. So the Ganymede orbits I'll show in a bit more detail on the next slide, but consist of multiple phases and will run for about 280 days in total. Not quite sure how this little movie is going to come out, so I put a static picture on the left to give you an idea of how that's going to work. We're going to have a dedicated Ganymede orbit, and this allows obviously the magnetic field, which is what I'm interested in particular, to be studied in great detail. And if you want to uncover the signal associated with an ocean, then it's required that we understand all of those magnetic field contributions that are present that I've just been speaking about and how they vary. So we need to understand the internal field, the magnetosphere field, how it changes, and then we may be able to extract the field due to an ocean, if it is indeed present. So the first part of the orbit then is an elliptical orbit with 10,000 kilometers away from Ganymede at one end and 500 kilometers at the other. And that orbit is designed specifically then to study that magnetosphere. This is just a sketch, by the way, so forgive, it's probably not entirely accurate, but you can see that it allows the spacecraft to pass through all of the key regions of Ganymede's magnetosphere, and as will the 5,000 kilometer circular orbit as well. And so these two orbits will really allow a good understanding and characterization of Ganymede's magnetosphere in better detail than obviously ever before. The final part of the orbit then is the close 500 kilometer orbit above, so it's 500 kilometers above the surface, so incredibly close. And this orbit will last just over 100 days, which is enough time to probe those expected frequencies of the magnetic field variations present. So I can remember a lot of discussion about how long was required and what was driving that. And to some extent, the magnetic field variations present were driving the amount of time that the spacecraft would need to be in that close orbit, measuring those weak magnetic fields due to a subsurface ocean. So JUICE is going to carry 10 instruments and 1 experiment to study the Jupiter system, and that includes the magnetosphere, the atmosphere of Jupiter, and also with this dedicated focus on Ganymede. And those instruments operate across 3 broad categories of remote sensing, geophysics experiments, and in situ observations of the space environment. So I don't propose to go through and read them all out. There's lots of really fantastic instruments on board, and I just would like to highlight the couple which I am personally very excited to be involved with. The first is the JUICE magnetometer, JMAG, and I'm going to talk about that in the next couple of slides. And the second is the ultraviolet imaging spectrograph, which is a US instrument. It's actually very similar to the instrument which is currently on Juno and performing absolutely fantastically. And their instrument has been on many other missions as well. So I'm very fortunate, I feel hugely fortunate to be involved in both of those instruments, which will allow me to hopefully use my expertise in both UV imaging and magnetometry to help the teams uncover some of the answers to these science questions that we have about Ganymede. Now, I wanted to highlight the JMAG magnetometer because this is the only UK-led instrument on JUICE. There are other contributions to hardware from across the UK, but the JMAG instrument is the UK-led instrument on the JUICE mission, and it's run from Imperial College in London, and the PI is Professor Michelle Doherty, who I'm honoured to say has been my friend and colleague for many, many years. And I was fortunate enough to work on the Cassini magnetometer team over many years. And she invited me to work with the team to define the instrument and to take part in the JUICE mission. So I'm really looking forward to that in future. And my colleague at Leicester, Nigel Bannister, also provided the radiation modelling for this instrument. So we have a good connection with our friends at Imperial. And as I mentioned, I'm also involved in the UV instrument as well. So many of the JUICE instruments are now delivered and integrated. I've got a little movie here which really does amuse me. I don't know, you won't be able to hear the sound. You'll have to go onto the web to hear this at your leisure. But this is a test of the 10.6 meter magnetometer boom, which has now been integrated onto the spacecraft. And this is showing the test of the deployment mechanism, which is a fantastic little film. And you can see it's being just held up by the balloons there, keeping it as if it was in space. But actually, what I really wanted to say here was to really highlight how incredibly hard the engineering team have worked throughout this pandemic. Michelle has told me that the team have worked through COVID safely and carefully, and I really think it's incredible that they've managed to deliver their instrument and others for JUICE during a global pandemic. That really is quite astonishing. And equivalently, the industrial contractor Airbus have also worked incredibly hard keeping the schedule going throughout this really difficult time. So I think this is a real testament to the team and how hard they work and how much they want the mission to be a success. And it's really fantastic to have seen that. Okay, so I'm just going to conclude the talk now by saying, I think pretty much exactly what we said when we gave this presentation at the ESA symposium for the L-class mission competition all those years ago. And we described the JUICE mission as our next logical step in exploration, following on from Galileo's discovery of the Galilean satellites over 400 years ago. And since that time, our knowledge of the large gas giants within our solar system has continued to grow. You know, we've had flybys from Pioneer and Voyager and Ulysses at Jupiter. And we've also had numerous ground-based and Hubble Space Telescope observations of the Jupiter and Saturn systems, which have taught us a huge amount. We have the discovery of deep habitats, deep habitable environments in ocean ridges on the Earth. We've had the Galileo mission exploration at Jupiter, and of course, the highly successful Cassini-Huygens mission to Saturn and Titan, which has now ended. Also, in relatively recent times, we've had the first discovery of an extrasolar water world. And so we really felt that this mission was the next logical step for us to progress from initial exploration to characterization. And that's what JUICE is going to do by studying the three moons in detail, and in particular, a thorough exploration of Ganymede, characterizing an entire class of planetary bodies. And it really is the mission to explore ocean worlds. We're also going to study the Jupiter system, which is like a miniature solar system in its own right. And we really feel that JUICE is the next necessary step for future exploration of our outer solar system and leading to possible landing missions in the future. So it's an incredibly ambitious mission, just as you would expect from an ESA L-class mission. And personally, I'm just really excited to see what discoveries this mission will bring in future. So I shall stop there and hand back to Carole, and I think I shall stop sharing my screen.
Emma, thank you. That was absolutely breathtaking. You know, we've got lots of really positive comments coming in the chat, and people wanting to watch this over and over again, which is streaming on YouTube. And so people will be able to watch it many times. I think what really strikes me is the incredible advances that has been made in this field. And I think it's the technology, the engineering, but actually, the physics of these planets. We're not just looking at them from afar and seeing how pretty they are. I mean, the incredible understanding that you're unraveling on the magnetic fields. So I've got a couple of specific questions I'd like to put to you. The first one is really around contamination and how will the mission, I mean, it's sad to talk about the beginning of the mission now and talk about the end, but obviously all of that goes into the mission planning. So a couple of questions, I have one from Marcus, one from Michael, asking about how JUICE is going to end its mission. And also, are you concerned about any risk of contamination of Ganymede after such a low orbit? So all of those sort of environmental questions really coming through in the questions.
Those are really good questions, because of course that's something that is very important, and the topic of planetary protection, I can get my words out, is an incredibly important topic. And for example, Mars and somewhere like Europa is categorized at the sort of highest level of protection against contamination. Ganymede is actually much lower, so it's less of an issue, I think, would be a way to put it. So the difference, I'm not going to start talking about Mars because I know nothing about it, so I'm just going to stick with something which I know vaguely about, which is Europa. The difference between Europa and Ganymede is the fact that we think, as far as we know, we think that the ocean, the subsurface ocean, which we're more confident exists at Europa, is likely to be interacting with a rocky silicate mantle underneath, a direct interaction between ocean and rock, which is more analogous to the situation that we have here on Earth. And so in terms of habitability, that means that it's felt that Europa ticks more of the boxes in terms of habitability. So in terms of thinking about habitability, you need to have the presence of water. So that's the first exciting prospect, that the outer solar system is swimming with oceans. There's more water on Europa or Ganymede than there is on the whole of planet Earth, if we've got the depths of these oceans correct, which is quite astonishing. But you also need to have the right chemistry, and you need to have stability over time, and you need to have an energy source, which I talked about in the talk. But the chemistry part is really key. So for Ganymede, we think there's the ocean sandwich, so the possibility of a thick ice crust. And then I didn't really mention this, but when you have ice at very high pressure, it's possible then to have a layer of ice that would effectively sink to the bottom of a liquid layer, because under high pressure, ice can actually become more dense than water, so it could sink. So you could have this ocean sandwich scenario, and that's in keeping with the gravity measurements. But we need more details. We need the JUICE mission to know more.
Yeah.
So that's a long-winded way of saying actually the habitability for Europa is probably more challenging. And how will the mission end? The mission is going to end by crashing the spacecraft onto
That's what I feared you would say.
I know, it's always a bit of a difficult thing. The end of the Cassini mission, I think we were all
kind of an emotional roller coaster for all of those scientists and engineers who've actually designed the mission and built their loving instruments and put them out into space.
Absolutely. It's an interesting thing that occurs when the end of a mission happens.
Yeah, I think Jupiter can cope. I mean, related to the habitability question, just let me ping this one to you. So this comes from Steve, who's asking, is there work underway to simulate Ganymede's subsurface ocean in the lab and to see what effects one might expect on life and the evolution of life forms, given that we can do this? Can we do this in the lab, and is there something we can learn?
That's a really interesting question. Certainly not in any of my labs, I'm afraid. But that's a really interesting idea. I guess it's the conditions would be quite difficult to reproduce because whilst we are talking about ice, it's not quite ice as we know it. It's ice at very, very, very cold temperatures. So it's a really good question. I suppose it is possible, given the appropriate equipment, that you might be able to do it. But I think it would be extremely challenging. But it's a very interesting idea.
Well, maybe Steve's got a lab and he can offer you access. I mean, maybe that we can take that offline and write a proposal. So an exciting opportunity. And then finally, one from Charles, which may be deceptively simple. What causes the tilt of Jupiter's magnetic field?
Oh, no, See, a few years ago, I think I would have said something along the lines of, I think it's expected from theory that actually you would expect there to be a tilt in the magnetic field, and that if you didn't, it would be highly unusual. But now, of course, we know Saturn's magnetic field is absolutely aligned with its rotation axis. And also, I think Mercury's magnetic field is very closely aligned to its rotation axis. So I think someone who's a little bit more expert on the dynamo theories, or theories for generation of magnetic fields within gas giants, which is obviously different to the terrestrial bodies as well, would answer this better than me. But one thing I would observe is that I think what's really neat about magnetic fields, I'm a magnetic field nerd, obviously, but every planet that we've visited, every spacecraft that has been to a planet has measured an entirely unusual situation. So it's not like we can say the planets in our solar system have magnetic fields that look in a certain way. Yeah. They all seem to have their own unique properties. So I'm afraid I can't answer that question very simply, but I'm sure a theorist would be able to.
It sounds like a new experimental frontier as well. So on that fascinating and open note, I would like to invite you, Emma, to a more relaxing setup with me by the side of the lake. Although it's warm weather, we will also have a roaring fire so we can have a proper fireside chat. And I'd like to invite the audience to join us for a wider conversation about science, society and careers in science, astrophysics and space science. Please join us. We will be moving now, literally in this minute. And again, questions and answers, do feel free to start to put those into the Q&A box. So bear with us as we move to the lakeside. Please join us. So welcome back. This is the next best thing to having a drink by the lakeside in a real conference. And thanks to our RAS colleagues for doing this wonderful technical wizardry. So what I'd really like to start to do, Emma, is, just go back a little bit. And you've told us this incredible story about where you are with JUICE and, some of the wonderful work that you've done leading up to this. And of course, you make it seem almost easy. And I know that, to get to this level of eminence in your career is no easy thing. So I'd love to kind of unpack that a little bit. And today, obviously, we've had two wonderful talks in our plenaries, in addition to all of the wonderful parallel sessions. And, Professor Dame Jocelyn Bell this morning gave a fantastic talk about, about women in astronomy and that long journey that we've been going on, and we still have very far to go, I think. And then in the afternoon, Professor Stefan Alexander was talking about, wider diversity and variety in science and the different kinds of minds and approaches and lived experiences that create a much better scientific environment as a human right almost that we have globally to be able to access and to think about and take part in science. So what I'd love to do is sort of take you back, and see your reflections from your experience, because you went to a single-sex all-girls school, and I'm just wondering, how do you see that in your journey? Did that give you the confidence to choose science? Do you think that was important, or do you have reflections looking back on the impact of that environment for your future career?
That's a really interesting question, because of course I didn't have any choice about that. So that was just the school that was closest to my house, and it was a single-sex school. It's a state school, but run by an amazing woman, actually, Dame Sheila Wallace. She's incredible, very strict, but really fantastic head teacher. So it's a really good question, because I have an experience that I would say that single-sex school was okay for me, was good for me. But I do also know that that's not the case for everyone. Statistically, I think we would be told that girls will do better in a single-sex school, but boys will do better in a mixed school. But I think it's more complex than that. It depends a lot on who you are, and it also depends on the school as well. So it's difficult for me to know if I was more or less encouraged into the sciences, because it's the only experience I had. And I would say that I was reasonably well encouraged at that school. There were some minor issues, but I'm sure that's true of every school. I think I was pretty much making the decisions for myself, in the sense that around about 14, I'd written off to NASA, inspired by the Voyager flyby of Neptune, to basically say, okay, you're going to need to tell me how I get that job. So I was kind of going under my own steam to some extent, but I think that I think that the school encouraged me. So going on from secondary school, I went to a separate sixth form college, where I was one of 4 girls doing A-level physics out of an entire class across the college of 55. We weren't all in the same class at the same time, but 55 people doing physics, 4 girls. And then my first year at university, there were 9 women out of a class of just over 100, I think. That was back in 1994, which I still think is recent times, but I do appreciate it's, a long time ago. So things have improved. I would say that on a good year, we might have up to 30% women undergraduates now. But it's not improved as much as we would like. I think we still see that there are, you'll have seen the data, the WISE campaign, for example, showing, that maybe 22% A-level physicists are women, and data showing that boys are 4 times more likely to do physics. So, but girls do like the other sciences. Biology, for example, is very popular. So, I don't know how much that is driven by the actual single-sex school or mixed school. I don't know what your feelings are on that. What do you think?
Yeah, I mean, it's really interesting, the statistics that you describe are sort of A-level, very similar for me. I mean, I was, one of 3 girls in a class of 40 boys in that particular, year group. And we were a tiny anomaly. The boys were equally shy as we were of us as we were of them. But it certainly sent a signal that it wasn't a subject. Physics wasn't a subject for girls, just subliminally. And yet it was a subject that I loved, and I was quite a stubborn personality. So I decided I was going to do physics anyway. But it's really interesting what you say at the age of 14, that, NASA caught your attention. You already had a pull through. So almost, maybe immaterial of the environment that you were in, unless the signals to not do this were very strong, you would have made it anyway. I mean, did you feel that as your journey through to PhD?
Yes, I was pretty focused. Pretty determined, stubborn. And I'm not saying this to sort of put myself down, because I don't think that's right, but I want to say it because I think it's important. I wasn't the brightest student, never have been the brightest student. And that's genuinely true. I used it as an example to encourage an undergraduate the other day, to tell them that, and I think that is important to say. So I'm not trying to put myself down, but it's just true. But I was pretty determined, and I knew what I wanted to do, and so I sort of carried on through, and I worked as hard as I could, but I also had great support, and especially as I got to university and going through the university system, then I had fantastic support for my PhD, for example.
It's interesting what you say about the determination, and Stefan said exactly the same thing this afternoon. I'm a dumb physicist, and I think there is this sense that to do physics you have to be a genius. There's some archetypal genius. I think we're all clever, and if we find a passion for something, the determination takes us through, because none of this is naturally easy. You don't build a space mission with that boom arm that you showed. That doesn't just happen through natural brilliance. That happens through teamwork and good project management and all sorts of different skills, doesn't it?
Well, I think that's exactly. I think you've really hit the nail on the head there, and I think that's one way that maybe the situation can be improved for the future, is about making the subject more accessible. Providing, perhaps alternative pathways through to the space sector, let's just say, as an example, and moving away from, but in addition to the physics and degree route, you can also have apprenticeships and different routes in that are perhaps genuinely more inclusive routes to working in our sectors, and that may be something, or I think it is something that really needs to be thought of in that way, and hence, you know, give it the value that it deserves in that sense.
I mean, I completely agree. I'm, you know, now with my new role as president of the Science Council, that's one of my two big objectives, are diverse pathways into science. And I spoke to some very inspiring apprentices the other day. And there's also the technicians promise that universities and actually, you know, private commercial organisations as well have been working together. And that's been really critical in keeping our labs open through COVID. And so I think you're absolutely right that just this idea you have a PhD and it's just one type of way in, I think is wrong. It's not accurate, it's not helpful. And actually, if I could just say on one technical issue, we're causing a bit of a stir by having caused a split in the space-time continuum. So we're going to do something very snazzy, and we're going to fix our fire by miraculously flipping simultaneously. And I think it's going to work. The particular peculiarity of Hopkins. So hopefully that will keep our Twitterverse happy. So we've done our technical bit, but you're absolutely right. I think those diverse pathways are really important, and it's great to hear you talking about them, because I think the more that we recognise those pathways, particularly because we're university teachers. I mean, you're head of a big physics and astronomy department. I was previously head of physics at Bath. Again, very anomalous for women to be heads of physics, but again, a new kind of icon that we're taking on those senior management roles. And I think, you know, do you see that there's big change that can happen there, or, you know, are there other blockages that we have to unblock to help those diverse pathways?
Oh gosh, that's a big question to unblock the diverse pathways. So I think you know what we talked about, different pathways through, for example, something like apprenticeships. But I would say that one of the good things about being a head of physics, and I will also add that it's been extremely challenging through a pandemic, as you can possibly imagine, and I'm sure we'll get to. I think you can make sort of small changes, and small changes can be effective. And it's just about always thinking about this in everything that we do, always thinking about equality, diversity and inclusion. And I'm really proud of the fact, actually, that physics and astronomy at Leicester really genuinely has that embedded throughout everything that we do. And I think that's a really very positive thing about where I work. And I hope that the people that work with me also feel that way. This morning, I thought it was interesting in Jocelyn's talk, she was discussing about the idea of, or the use of double-blind applications, for example, when hiring. So I think that's a really interesting or really important factor. And I also think that things like search committees for jobs are also vital. So if you have a role coming up, a leadership role, let's say, then you know, there is an opportunity there for the university to go out and seek diversity and seek a diverse pool of candidates to apply for the job. And then you're on a level playing field as you come in with your application, of course, but you may be encouraged to go for a role that you perhaps otherwise wouldn't have felt that you would put yourself forward for. And I think that is happening. And, you know, I think that does happen more and more. So I think also those sort of small changes are positive too.
I think you're right, being very conscious about it. And, you know, if you don't get the applications, then you can't shortlist them. So it is actually that diverse reaching out and saying, put your application in and give us the chance to use our good ED&I processes. Yeah, absolutely. And, you know, I'd like to sort of get on to recognition, because I think that's also part of our systems. Obviously, everybody likes to win an award or be recognised. And you've won a number of prestigious awards in your career. I mean, it'd be interesting to hear you reflect on what impact that had on your career. I mean, I've heard people say, oh, Nobel Prizes are too male dominated, we shouldn't have them anymore. And so there's quite a debate about the systems, or, you know, whether awards are good or bad. I mean, you know, I think there's all sorts of ways we can provide recognition, but I'm really interested to hear your reflections as an award winner, and also as a president of a major society that awards recognition in this way.
So okay, let me try and answer that sort of relatively briefly, because I could probably go on for a while. But so personally, the impact of prizes, I would say, obviously for me personally, was really encouraging. Whilst I might be stubborn and determined, I'm perhaps not the most confident person. So actually to win something, for example, I was awarded the RAS thesis prize back in 2002, I think, just after I finished my PhD. And that was really amazing to think that my work has a small impact, and that other people have read my thesis outside of my supervisory team. So that was really positive. I was so happy to receive that. It was magnificent. And other things, I was given a Belgian prize at one point, and I found out that I was nominated by some colleagues that I'd met and was working with from Liège, and I just thought it was incredible that they could actually take the time to write a nomination. So I think that sort of thing, you think, well, that's really great. And for me, I would say it provided a bit of momentum, so encouragement, maybe a bit more confidence. So I would say, almost entirely positive, although there is one small negative, but maybe I won't mention that. So I think from the RAS perspective, we've been looking at the awards. We've been doing a review of recognition, actually. So we've been looking at exactly this topic with a view to really understanding what recognition should look like in 2021. And whether what we do currently is reflecting, how we think that recognition should look, and are people being rewarded for the work, the fantastic work that our community does in so many different ways? Are we reflecting that in the prizes and awards that we have? So we've certainly been looking at that, and we're planning to put out a report on our findings. But interestingly, we did a very quick survey of our membership, and I have to say I was so encouraged that it was a very quick turnaround. We were working to a short schedule, but we managed to get 700 responses or something to our survey, and I was really impressed that our membership, our fellows, were so engaged with that, and we've got some really interesting viewpoints. And on the whole, I don't have the numbers in front of me, but on the whole, I would say that there was an overwhelming feeling that the recognition process was really important for all of these reasons, to encourage people, and to give people opportunities through having been awarded prizes. And all sorts of other positives as well. So
I think it's great that you're looking at it in that detail, because you're right, actually, to be nominated is already a great recognition, and when it's your colleagues who've respected your contribution, I think it can be really uplifting, a confidence boost, really touching. And I think it's great that you're looking at it in the round to keep it modern and progressive, I think, for the 21st century. So let me touch on, I'm mindful of time, and I know we could chat for hours. And a couple of things I'd like to do is touch on your role as RAS president and some of the bigger reflections that you have. We're at this iconic point where we're 201 years now after the founding of the RAS, and you are the bicentennial presidents, no pressure. So just, what are your reflections? What are your thoughts, our community, look to the future?
Yeah, all really positive. I wasn't expecting a global pandemic. So one of my colleagues at Leicester, but of course none of us were, one of my colleagues at Leicester said to me, "You'll be the first virtual president of the RAS." And I think it actually may well be true at the rate that we're going. I hope not. I do really exist. I'm not a hologram. So it's not quite been what I was expecting, obviously. But it's been a lot of fun so far. I can't believe actually that I've got less than a year left now. And it's really an honour to be in this position. It's a lot of fun, it's a lot of work, but it's really great, and it kind of takes me into working in different areas and new areas that I wouldn't necessarily do otherwise. In terms of things which we're doing, which I think are really positive and that we should continue to do, are things like looking at research culture and asking questions about that with our surveys, and actually later in the week there's a session on Thursday about the bullying and harassment survey, which is going to be presented, which is a pretty somber look at the research culture, and so we need to do things like that. We need to think about things like that, and then we need to act, and we need to make sure that it's communicated to the community. I think the RAS has a really important voice there, actually, within our community, because we're sort of free of institutional baggage. And I talk about wearing different hats, and I think that's really absolutely key, that when I've got my RAS hat on, I've got my RAS hat on, and it's not the same as when I've got my University of Leicester hat on. So I think that's really great. One thing I wanted to just mention to you actually, which is really positive this year, we actually have, possibly for the first time ever, the same number of women and men on council. I'm not sure that's ever happened before, so I think that's pretty positive.
Congratulations.
So I think that's
a milestone.
It's really good. I think that's really good, and it's great to see everybody putting themselves forward to be part of the RAS Council, because it's the society for the community, so it's really important that I do that. Another thing, just quickly, that we're doing is we've created the new Early Career Network, and I think, again, I personally feel very strongly about supporting our early career scientists, postgraduates, postdocs in our field. So it's been great to get that off the ground. And then, of course, the other new exciting thing which is happening, which I have to mention, is the fact that we are launching a new journal. And that is going to be the first new journal for nearly 100 years. So I think it's really fitting that that's happening now, approximately in our bicentennial year. And the topic is going to be, it's going to be an open access peer-reviewed journal on techniques and instruments. So it's a really exciting opportunity to publish papers on topics in astronomy and geophysics, about instrumentation, data science, machine learning, software, etc. So really looking at those subjects which are developing and becoming more and more important in our research. So I'm really excited that that's happening very soon.
That's fantastic. And, you know, as a virtual president, you've achieved so much already. I think it's great to hear that combination of those new frontiers coming through and that recognition within the journal, the work you're doing on awards and recognition. And then I think the culture piece is really important, because it's one thing having diverse pathways into science. But of course, if we drive people out because of, you know, hostile workplace environments and harassment, then that's a failure. And so I think it's great that you're able to take all of this in the round. And I think that should move our field forward. So I know we go to, you know, both of us do a lot of work on, you know, diversity in STEM and women in STEM. And actually, when you go into school and speak to young girls and say, yes, you should come into this field, we have to make sure that the whole field is, you know, is safe and productive and, you know, a thriving place for everybody, whatever their background is, whatever their lived experiences, that they feel that there is a place for them in science. And I think that benefits us all. Actually, it benefits every one of us, and to have that improvement in culture. So it's great to see you and the society leading on this. You're absolutely right. You have a very different role to anybody, whether that's institutions, government, funding agencies. You actually stand. And I think that's internationally, we see this with learned societies around the world really gripping this tricky problem, because we work internationally. It's an international collaboration.
Really, really important. And I would just say I could not possibly take the credit for all of those things. It's a huge team effort, council and the fantastic RAS staff all working together. So it's been, you gotta say, it's been fun. It's been hard work, but it's been fun.
We'll look forward to that session later in the week. So I think in the last few minutes, what I'd really like to ask, I think is you personally. So, you know, you're an eminent scientist, an eminent space scientist, you're an incredible leader and manager, and you've got all this wonderful CV. And so how do you balance that with family life and you time?
Gosh, it's a massive challenge, if I'm just going to be completely honest with you. It's always been a challenge. I have 2 children. And I think that has obviously given some extra challenges to all of that balancing act. So it's been tough over the years. My children are now teenagers, so actually relatively quite a lot easier. Those early years, balancing small children, working, trying to sort of establish myself in my career with very young kids is very hard, and I'm sure a lot of people will relate to that. And it's a big responsibility raising teenagers in our society, isn't it? So you know, there's a lot of work to be done even when they're older. You know, you can't just let them get on with things. So I always try to just balance things the best that I can. I mean, you know, I always have a rule that when I finish work in the evenings, you know, when I do finally shut the laptop, and sometimes it might be quite late, I don't go back. I don't think I'm coming back at 10 o'clock to read my email. I just shut the laptop and everything can wait until the next day, because for me, I think it's just the way I am, and everybody works differently. But I need to kind of have that break and have some time with the family, and I try to do that. And same at the weekends. But it's been difficult, and I think with COVID it's been extra difficult because of the extra worry, and there's been a lot of extra worry, especially running a physics department. What about you, Carole? Because you're the same. I mean, you have this amazing position at the University of Bath, you're science advisor to the Foreign Commonwealth Development Office, president of the Science Council. How do you fit it all in? We should perhaps give each other tips. What do you think?
Yeah, I think so. And I think one of the dangers is that, as young people coming into the field, they look and they say, well, they don't have any problems, or it's easy for them, or, also you don't want to moan too much because what's the point? Why are they doing the job if they hate it? No, I mean, for me, I've got 2 children. They're both teenagers now. When they were very young, I was actually building my research group up at Liverpool John Moores University. We were literally trying to design the systems that would catch gamma ray bursts in the middle of the night. So my newborn babies were sleeping through the night, and I was up in the middle of the night chasing the birth cries of new black holes, which was incredibly exciting. Yeah, exactly. But it was incredibly exciting. But what I think enabled me to do that, I had a research fellowship, and I had the real flexibility. So I think not having the 9 to 5 at your desk was hugely enabling for me, because we were all doing the science in the middle of the night. It was exciting. And then I would say to my postdocs and students, well, I don't expect to see you at the desk at 9 because you've actually been working at 4 a.m. We would negotiate paper leadership in the middle of the night. So very exciting. I have to say I was younger then. I don't think I've got the stamina for that now. But actually, splitting my work, I think, between academia and government has also given me a really fresh perspective. Very different timescales. The pace at which we work in government is very different. There's lots of interesting ways of working that I'd like to bring back to academia, and vice versa. And then I think finally in this COVID year, I think it's been challenging for all of us in all sorts of different ways. But one of the things that I think has got me through the dark moments is being able to connect internationally. And that's part of my Foreign Office work. Meeting digitally, which is something probably previous generations have never been able to do, but speaking to people around the world and helping one another, because this is a big global problem. And to be able to compare science, to compare processes, to just compare notes with people around the world, I think has been hugely inspiring. And, just a huge testament to the scientists who've got us to the stage in less than 2 years to have vaccines at scale, which was something we could not possibly imagine would have been possible at the beginning of our SAGE journey in January 2020. It was too much to hope for almost. And I think to see that science infrastructure from the scientists in the lab through to the innovation at the engineering frontiers that we need to have to go from the first vaccine to the billionth, it's just a huge innovation pipeline, be it logistics, be it our health services, and building that trust in people to come forward for their vaccines, because that's also a big step. So if you haven't had your vaccines, go get them. They are a miracle of modern science, and they're what give us the lives that we have now. So, for me, really privileged to be able to work at that frontier through this really tough year.
That's incredible. And the thing that we're seeing in applications coming through this year is that there's a definite uptick in the medical sciences. And I think that's a direct response to that, really inspirational reaction from medical science to actually solve those vaccination issues so quickly. And
it's actually been interdisciplinary. I mean, I have to say that the science, the physics, the engineering, the virology, for me, it's been massively interdisciplinary. And that, exactly. Everything all the way through. So science, engineering, innovation. And it's great to have this week to talk about astrophysics, all safely where we are. And actually for a little while, just switch off from pandemic and pandemic planning. Absolutely. And think about the frontiers of the universe.
Couldn't agree more.
So thank you so much for your time. It's been a real privilege talking to you. I know we could have gone on for hours. I will have a cool drink, I think, away from our warm fireside. And I would now like to thank you again, Emma. It's been wonderful. Everybody can see on YouTube, watch this all over again. And I would now like to invite Phil Diamond, who is the Director of the Royal Astronomical Society, to close our session. Thank you.
Thanks, Carole.
Good evening, everybody. It falls to me to close the evening by thanking Emma for her really fascinating presidential address. She's had to wait patiently to give it, but it was certainly worth the wait for all of us, I'm sure you'll agree. And thank you, Carole, for chairing the conversation this evening and for co-chairing the conference. I have to say, Emma and Carole have been our experimental probes for an entirely new form of presidential address, but I think it's been a successful mission. I also want to thank Lucinda for such a sophisticated production this evening. It's been great. So it's been a fantastic first day, I'm sure you'll all agree. That's down to the speakers, the local organising committee at Bath, who are working hard every minute of the day to give you all a good experience. And for you all delegates, for engaging so enthusiastically with the programme. I won't keep Emma and Carole from their dinner now, which has been gently barbecuing on the fire behind them. So please enjoy the rest of the conference, and I look forward to seeing you during the week. Thank you.